So let's go on page 103. Now, we're talking about angular and linear velocities. What's another word for velocity? Speed. Yes, y'all learned physics, right? Speed. Okay. So, velocity and speed, same thing. Okay. So we have angular velocity and linear velocity. The most generic that I can get velocity, and it's something per something, which means it's a kind of a ratio here. This is just angle per time, because the angle can be measured in degrees, radians, or revolutions, and time can be hours, minutes, seconds. So it could be degrees per second, it could be radians per minute, it could be revolutions per hour, but it's some sort of angle measure per the time, right? So when you set that up, that pretty much tells you how to set up your little equation. And then we have this thing, which just looks like a more curvy W. Anybody know what Greek letter that is? It's omega. Good. It is the Greek letter omega. It just looks like a fancier lowercase w. So W, which is omega, is the angular velocity. I'll just abbreviate it VEL, so there's not really much written there. Theta is the angle measure. And T, of course, is time. All right, but again, the angle could be in degrees, radians, or revolutions. Time could be in hours, minutes, seconds, or whatever. But so when you put it on there, you have to make sure that you have the units correct that you're talking about. So this tells me right here then that my little formula is just that the angular velocity is equal to theta over time. Okay, degrees per second, revolutions per minute, whatever. So 1 revolution would be how many radians? 2 pi, right? Because it's 360 degrees or 2 pi radians. So this is 2 pi. How many times does it revolve? Okay, so then we have linear velocity. Linear velocity is more like a line. It is still speed. But now we're talking more of a distance. So linear velocity is distance per time. Okay. And you can use the angles or the angular velocity to help you calculate the linear velocity. And if so, then it must, the angle measures, so if you're using for linear velocity, then the angle measures must be in radians. So, and again, distance could be in inches, feet, miles, or whatever, and then here's some simple conversions that we absolutely have to have, right? So you can use the angular velocity to get the linear velocity. If you just take that, and the reason that your angular velocity would be different, okay, because if I go one time around, that's 360 degrees, be different. It changes based on how long the radius is, right? So if your radius changes, then your actual distance you go around changes. Does that make sense to you? Right? A bigger tire, takes longer to go all the way around than a smaller tire, that sort of thing. So in order to figure out what your actual velocity is, your linear velocity, you could just take your radius times your angular velocity, which is W, right? So what is your angular velocity, remember? So that would be velocity equals R times, and then this is just theta over time. What is R theta? What is that an equation for? Arc length, right? Isn't that the arc length? That's the S. So your real velocity formula, your linear velocity formula, is arc length over time, S over T. And that's where, because that's your distance, because that right there is a distance instead of an angle. So your distance over time, and that's where theta comes into play. Even though we're talking about distance per time, you're going to have to use that. So if you're going to use your angular velocity, it would have to have been of radians. Or if you're coming up with the arc length and having to do R theta, then you're going to have to make sure that your theta is in radians. Okay, does that make sense to you? We're good? Okay. I always take your blank stares as sure. That's good. All right, so then we have the front and rear tire of a tricycle. So I'm not even going to try and draw a tricycle, but what's the difference most of the time in the front and rear tires? The size. Like this, the back ones are smaller and the front ones are bigger. So it's something like that if you look at it from the side, right? Okay. So it says the front and rear tire of a tricycle would have the same blank velocities but different blank velocities. So do you think that these two tires, so I'm just going to draw my little radius here. Which velocities do you think would be the same, the angular or the linear? If the angular, that means it would take me the same amount of time to go all the way around this one as it would all the way around this one, right? But if I'm riding my tricycle, right? Are they covering the same amount of ground? They are. Is one of them turning faster than the other? This one's turning a whole lot faster, right? It has to, because it's going to have to go around more times. Like if you have short legs and you're walking with somebody with long legs, right? Aren't you like, it's like you're walking like twice as fast because you're trying to keep up. Some of y'all are laughing because you're like, yes, me every day, right? So you're trying to keep up because they're just like walking at a normal pace, but their legs are longer, so they're covering more ground. So same thing here. This one's covering more ground and not having to spin quite as fast, and then this one is spinning a whole lot faster. Okay, so it has the same linear velocity, but different angular velocities because the revolutions per minute would be different. Okay. So then we have 2 points placed on a ray drawn on a record. Okay, so here's my record, here's my ray. So here are my 2 points. I've got this point, no, not that point. I'll do like this point here and this point here. So those 2 points on that record, when the record's going around the little record player, right? Are those going to cover the same amount of ground in one revolution? Think about that. When this one goes around, he's going around like this. And this one's going around, do they cover the same amount of distance? No. Okay? This point's covering more distance than this one is in one revolution, right? So they have the same, would have the same angular velocities, but different linear velocities. This point is going to have to go a whole lot faster to cover the same amount of ground. Okay, so do you see the difference between the angular and the linear? It's like how many times it goes around, and then the other one is how many, or how much ground it actually covered, the linear part of it, in feet, inches, or whatever. We good? Yes. So let's see. It says find the angular velocity in radians per second. So it tells me what to do. Radians per second of the second hand of a clock. Okay, so that reminds me. Shelby's question yesterday, which was a really good question. And so it was just like on my mind, and I couldn't let it go. Like, why? Because you're right. If you're rotating around a clock, it's clockwise. So it's a negative angle. But if you're starting at noon, right? You're basically starting at 90 and then going. And that angle isn't even in standard position. So we're not necessarily using standard position angles. That's why the sign doesn't matter. It's what is the angle measure. And if you're just looking at the angle measure and it's not in standard position, then that's more of a positive thing. Does that make sense? Because that was bugging me. Like, there's not any little disclaimer in there, and that's what it is. No matter what time it is, I can still go 90 degrees or whatever. It isn't necessarily in standard position. So I'll go either way. It's just how far did I go, or how many degrees or radians. That's a good question. All right, so find the angular velocity in radians per second of the second hand of a clock, and then express the answers in terms of pi. Okay, radians per second. So how many radians how do I figure that out? Radians per second. So I'm looking for, this is angular velocity, right? So that is my omega equals theta over time, right? And I know that it's supposed to be radians per second. So, in one complete revolution, how many radians is that? 2 pi. And how many seconds is that? One complete of a second hand. How many seconds is that? 60, yeah. So these are not really difficult questions here. So this is, when I reduce that, I get pi over 30 radians per second. You see how that works? And then it says find the angular velocity in radians per second of the minute hand of a clock. Okay? Minute hand of a clock. So it's still velocity equals theta over time. This time I need it in radians per second, but I'm looking for the minute hand, right? So how many seconds are in a minute? Oh, I already did that. The minute hand of a clock. Did I do this wrong? Oh, no, that's right. Okay. Hang on. Oh, God. Clearly I didn't work this out beforehand. Two pi radians is 60 seconds. 2 pi radians is still 60 seconds. Oh, God. Can I get this one? This is why I don't even want to put this on the test. I can't even think through this. I can't think what the conversion should be. Well, because it says radians per second. Say that one more time. Oh, it's 60 minutes. Thank you. God. Okay. Yes, I know. That's why I'm thinking the minute hand is slower. There is something off here. So, yes, it takes 60 minutes. Thank you. See, I can't even think about a clock. Okay. To make one, because you have to think one revolution. Okay. Oh, my Lord. I'm sorry. One revolution equals 60 minutes. Thank you. All right, so one revolution equals 60 minutes. And I need to convert that to seconds. That's what I was trying to do in my head. Okay, so then that means that one revolution of the minute hand is how many seconds? 3,600, thank you. I was like, how do I get that number? Oh, my God. All right, so 2 pi radians, 3,600 seconds. And then that reduces, right, to pi over 1,800 radians per second. I really did not plan on winging this, guys. I couldn't even pull it out of my bag last night, and I didn't get here until right before second period started. So, okay, everybody okay with that? Thank you. And I'm skipping this one. I want to do the next one because I don't want to spin forever on these either. All right, Ferris wheel problem. Dandruff and Elephant, it's cute, right, are riding on a Ferris wheel. Dan observes that it takes 20 seconds to make one complete revolution. Their seat is 25 feet from the axle of the wheel. What is their angular velocity in revolutions per minute? Okay, so we've got this 20 seconds thing here, and I want revolutions per minute. And so here's my Ferris wheel, right? They are 25 feet from the center, so that is my radius. Right? So I'm first looking for my angular velocity, right? And so my angular velocity is theta over time, and it's asking for revolutions per minute. So my theta is my revolutions, right? So I'm going to put my little units in here so I can make sure that revolutions per minute. But what they give me is this 20 seconds, so I need to convert that. Okay, I need to convert the 20 seconds into minutes. So 20 seconds equals how many minutes? How do I figure that out? Is it going to be more than a minute or less than a minute? Less than a minute. So it would be like 20 over 60, right? So a third. Okay, so it's a third of a minute. 20 seconds equals 1/3 of a minute. So one revolution takes 1/3 of a minute. So how many revolutions per minute are there? 3. So this is 3 revolutions per minute. Okay. If I want to do degrees per minute, okay, degrees per minute, then 1 revolution is how many degrees? 360 over how many minutes? 1/3, right? So basically, aren't I just multiplying the 3 times 360? What's 3 times 360? 1080, right? Yeah. You're confusing me with the 9 there. Okay. Degrees per minute. Radians per minute. 1 full revolution is 2 pi radians over 1/3 of a minute. So that's going to be 6 pi radians per minute. So if you just have the revolutions, and you know how many revolutions per minute? The conversion from revolutions to degrees and radians, you're basically just taking whatever your revolutions per minute is, multiplying it by 360, multiplying it by 2 pi, whatever it happens to be. Everybody okay with that? So now it asks for my linear velocity to the nearest foot per second, okay, which means we're going to be able to use the calculator here just a little bit. But if I'm going to do linear velocity, my linear velocity is equal to arc length over time. I can go and I can find the arc length. Is arc length something we already know? I mean, do we have it? Have we found it yet? We haven't. Now, this is your formula, but remember, another way to look at arc length is just r theta over time, right? Because arc length is r theta. And do you already have theta over t? Because what is theta over time? It's your angular velocity, right? And if I'm going to use that, which one of these 3 do I have to use? If I'm going to have to use theta, it has to be in radians. So I'm using this 6 pi. So my radius is 25 times 6 pi. You could go find arc length and do r theta. You're going to get the same thing, right? And then that's going to give me, and that was in feet, right? I'm going to double check. Okay. So when I multiply that, and you can, it says, I didn't even bring my calculator up here. You're going to have to help me out. So it's the nearest foot per second. What is that? 150? Oh, well, now my calculator disappeared, so that's about, what? 118? 115? Oh, I'm sorry. I thought you were multiplying the pi in. I was like, it is not 150, guys. Okay. Well, since it says the nearest foot per second, we're going to multiply the pi in. I'm sorry. I should have made it more clear. Yes. 6 times 25 is 150. Like, I can actually do that one without my calculator. With the pi in there, what is it? Sorry. Okay. All right. So now remember, we're always supposed to do everything to 3 decimal places unless it says otherwise, and it says nearest foot per second. So this is going to be 471 feet per second. I didn't know what it was without the calculator, but I knew it wasn't 150, so I was confused. All right. We all good with that? Oh, shoot. Yes, thank you. Oh, my God. Okay, it says revolutions per, I was worried about the feet, and it says per second. So this is not my right answer, right? I just have to take this. That is, well, that's my right answer for feet per minute, because we used per minute. Yes. Dang it. Guys. You're probably better off teaching yourself these last few weeks. 7.8, oh no, 8, it's just 8. 8 feet per second? Yes? Yes, yes. That's actually my answer there. So it's to not confuse yourself with all of that. Well, first of all, you probably should learn from somebody other than me, but you could also just do this from scratch so you're not having to convert that way. So if we do r times theta over t, right? And since we want it in, so let's look at that one. So if I just do velocity equals s over t, which is the actual formula, which is r theta over t to break it all down, your radius is 25, right? Your theta is the 2 pi, and then your time, since we want it in feet per second, then that right there, those seconds, that's going to be your 20 right there, and it should come out to be the same thing. It does. So you can do it all from scratch. Instead of using your angular velocity, I wanted to show you how you could use your angular velocity, but I think that made things worse. 8 feet per second. You just got to make sure you handle it right in the calculator. I really do know how to do this stuff, but I can't even. I'm lucky I got myself to work today. All right. The rear wheels of a tractor are 4 feet in diameter and turn at 20 RPM. All right. So I tell you what. Why don't you start working through these? I'll give you a second to work through them. And all right. So it says the rear wheels of a tractor are 4 feet in diameter and turn at 20 RPM. So your 20 RPM, this is your angular velocity in revolutions per minute. We are looking for nearest foot per second, which means we need the linear velocity, which is the arc length over the time. Now, in this case, we have the angular velocity. If we just convert it correctly to what we need to convert it to, then we'll be fine. Now, it says per second. This right here, what we have is 20 revolutions per minute for every 1 minute, right? That's what they've given us. We want it in seconds, and we need it in radians in order to use it. Does that make sense to you? So that means that we know that 1 revolution is 2 pi radians. So if we have 20 revolutions, how many radians is that? It's 40 pi. Yeah, we multiply it by that. And that's radians. Okay, does that make sense? Because 2 pi radians is 1 revolution. So if there's 20 of them, I got to multiply it. And I don't want it in minutes. I want it in seconds. So if it's 1 minute is how many seconds? 60, which is what I was trying to do on the other page and couldn't even have that thought. So that is my angular velocity there. That is my theta over time. So this s over t can be just my radius times my angular velocity, because this is theta over time here, right? It's the same thing here. So that means that what is your radius? 2, because that's 4 feet of a diameter. So radius is equal to 2. So this is going to give me 2 times 40 pi over 60. You can multiply all that out on your calculator. And it says nearest foot per second, so I get 4 feet per second. You agree with that? Okay. Everybody okay with that? Okay. So then it says the front wheels have a diameter of 1.8 feet. What is the linear velocity of a point on those tires? What do you think I need to do here? Nothing. Well, check this out. We've got, this is like the tricycle, right? Our angular velocity is different because isn't the smaller wheel going to spin faster? Do they cover the same amount of space? Or the same amount of distance is what I mean. They do, right? So their linear velocities are the same. If not, the tractor would have to stretch out or something like that because it wouldn't be covering as much distance, all right? So the answer is 4 feet per second. But in order to, and I should have done it on this calculator. Let me get this up here. It was, oh my gosh. I'm sorry, but I have to keep my ringer on too, but of course I'm getting a bunch of stupid things. All right, I had to do 2 times 40 pi divided by 60. Okay, that's where I got that from, right? Okay, so that's where that 4 feet per second came from. Then when we look at this last one, it says, what is the angular velocity of the front wheels? So the angular velocity of the front wheels, and with our front wheels, the diameter is 1.8 feet, which means the radius is what? It's just 0.9 feet, right? Okay, so the radius is what we really need. But we want the angular velocity. Well, I know what the linear velocity is. So in my calculator, though, because I rounded, I've got to store that. So I'm going to store that. I'm just going to store it in X, because that's the easiest place to store it. You can store it wherever you want. You can store it in V, because it's velocity, whatever. So I've got that. Now, if I just set up what's happening here, just like here, it's the same formula. The velocity is equal to the radius times the angular velocity. In this case, we know what the angular velocity is. I'm sorry, we know what the linear velocity is. It's 4.1 something, because that's in the calculator. That's equal to the radius, which is 0.9, times the angular velocity, which we don't know. Right? So all I have to do is, and I didn't necessarily have to store it as long as I didn't hit clear, I've just got to divide both sides by 0.9. So if I take what I have here, and I divide this by 0.9, that is my angular velocity. And so this is W equals 4.65, 4.65, But that is, what are the units on this? Radians per minute. I don't want it in radians per minute, right? I want it in revolutions per minute. How do I get this from radians per minute to revolutions per minute? Divide by 2 pi. Because if it's in radians, remember how I got to radians right here? Okay, I had to take my revolutions and multiply by 2 pi. So to get from radians to revolutions, I have to divide by 2 pi. And when you do that in your calculator, be careful, because unless you have one that's going to put that stuff in fractions for you, I'm going to divide it by, I have to open my parentheses, 2 pi, and close my parentheses, and then bam, 0.741, and it doesn't say like to the nearest whatever, so we're going to go with 0.741 RPM. Ugh. Y'all agree with that? Mm-hmm.
How did you go from taking from the linear with the S bar like T to radius times?
Because S over T, the formula for your arc length is R theta over T, and theta over T is that. So they kind of all, you kind of need to understand the 3 of them depending on which pieces you have, just know how they go together. Now, I do realize this is probably one of the worst lessons I've ever taught in my entire life, okay? And that's saying something, because I've been teaching for a really long time, okay? So I don't want you to stress out over this. I gave you a really bad examples that I couldn't even get through, okay? And I'm willing to say this, I'm still recording, and it's fine. I'm leaving the questions on the test, okay? Like, they're there. You don't even have to do them. They'll maybe be bonuses if it makes sense. If none of this makes sense and you can't do the homework, we'll talk about it again on Monday, okay? So it says it's due on Monday. Don't worry about it, all right? Maybe by Monday I could have a complete lucid thought, and maybe you could know what questions to ask, and I will make all this right, I promise, okay? You just got to bear with me. I'm just making it through the day these days, okay? I'll make it fair, I promise. I'm not going to make it hurt your grades or your understanding.